our first thing that we are going to look at today is a generalization of the problem of Deutsch. And there the idea is to get so first of all, we want to get a large separation between classical and quantum. So get a large separation between classical and quantum. So what we do is we consider some function. And so remember last time we looked at binary functions of 1 bit. And now we are going to look at binary functions of n bits. Okay, so this notation here, maybe it's better like this. So this notation here means that this is an n-bit string that the function takes as input, and the output is just binary. And so the problem is defined now like this. So find out, or perhaps let's say like this. So given an unknown function, f, find out whether so f is constant. So constant is just the direct generalizations what we've seen before, the last time. So it means that f is equal to 0 or fx is equal to 1. Sorry, my notation is not great. So so either we ask that fx is equal to 0 for all x, or fx is equal to 1 for all x. Okay, so the function is just constant. And so the second point, so remember last time we had to decide whether the function was constant or balanced. It's actually going to be the same here. But of course, for the class of functions that we have now, we should first clarify what it means balanced. And so what balanced here means that f of x is equal to 0 for exactly half of the possible inputs x. Okay, so there are 2 to the n inputs. Okay, it's the number of bits string of length n, and exactly half of these would give me f of x equals 0. The other half give me f of x equal 1, and that I call a balanced function. And so something to notice here. So when we define this, we have the promise from the beginning, right? That f is either 1 or 2. Okay, so it's either constant or balanced. Of course, here there are functions which are not of that type, right? Well, n equal 1, as we discussed last time, then a function is either constant or balanced. There are no other possibilities. But of course, when n is larger, well, you can have functions which are neither constant nor balanced. But here we just ignore these, right? We are giving a function which is either constant or balanced, and our goal is to find out which one it is. And so that is a first remark. And there is another remark, is that no errors are allowed. Okay, so we want an algorithm that solves the problem deterministically without making any error. Okay, so any questions so far? So first of all, we should discuss a little bit what is the situation classically for solving this problem. So classically, in fact, the result will be pretty easy to understand, although it's pretty hard no, sorry, is it hard to demonstrate? No, it's probably not very hard to demonstrate, but at least it's very easy to understand. The point is one needs at least 2 to the n minus 1 plus 1 evaluations of the functions. Okay, and I remember this is a type of problem that we called an oracle problem. So we are given a box, and this box implements this unknown function. And so what we can do is we can use the box to implement the function on any desired input. But each time we use the box, we pay a price. Okay, we pay 1 franc, let's say. So of course, this is a specific type of problem. It's arguably not the most general type of problem, but in a sense, these oracle type problems, they are very convenient to formulate these simple examples here. Next time we will go to a problem that is not an oracle problem. That will be the problem of factoring. But for now, we stay with oracle problems. So here, so classically we say we need this number of evaluations of S, and the number of evaluations of S is the uses of the oracle. Okay, so this can be thought as a time resource somehow. In each instant of time, you can use the oracle only once, and therefore, if you need to use the oracle many times, it takes you more time to solve the problem. Now, why is that the minimal number of uses of the oracle? Well, the idea is that, so intuition. So notice that this number here is, so 2 to the n minus 1 is half of the number of inputs, and to that we add 1. Okay, so this number represents the majority of possible inputs, but is the smallest possible majority, right? You are at half and you add 1. So the intuition is that if we would use only 2 to the n minus 1, so 1 less than here, so for 2 to the n minus 1 evaluations, damn it. Okay, good, that was easy. So for 2 to the n minus 1 evaluations of the functions, so there is always a small probability to get it wrong. Okay, so you see, so if I evaluate the function on 2 to the n minus 1 inputs that I choose at random, okay, so if the function is constant, then all the outputs for these inputs will be, say, 0, right? Now, so that is a strong indication indeed that the function is constant. However, notice that it could still be that the function is balanced, because maybe these 2 to the n minus 1 inputs I chose at random, maybe they are just exactly those inputs for which my balanced function is 0. Okay, so that, of course, it has a small probability of occurring, but it's possible. And because I do not allow any errors here, so using the oracle only 2 to the n minus 1 times is not enough. Okay. However, if I use it once more, then I'm good. Okay, because if I have tested the majority of all possible inputs, and if these are all 0, then the function is constant. Okay, it could not have been that the function is balanced, because I have tested a majority of inputs. And if the function is balanced, well then, among all these evaluations, there will be at least an output 0 and at least an output 1. And therefore, I know that the function was not constant. Okay, so that is, I guess it's clear. And I think contrary to what I said before, this is easy to prove. I think what I just said is basically the proof. Now, what about quantum mechanics? Here, well, we will see that in fact only one evaluation is enough. Okay, and that is true for all n. Okay, so here this is getting better, right? So here we have an oracle problem which needs exponentially increasing number of uses of the oracle classically, right? But quantum mechanically, we can do with just one, okay? So here is how to do it. So this is, let's say this is the generalized Deutsch-Jozsa algorithm. And it goes like this. So here I have my oracle implementing the unknown function. And so as usual, I start, okay, I would start with 2 registers. And on the first register, I will essentially make Hadamards. In fact, here I will not describe the circuit into too many details because it's just a direct generalization of what we've seen before. So the point is, I'm interested here in the state at the output of the problem. So this is my output state. And I will rewrite it here again. And this output state depends, of course, on the function. So I write it, I don't know what this letter is, xi, maybe xi of f. And essentially, you remember, so the idea was that I first have this huge superposition of all possible inputs. So I have a sum here over x going from 0 to 2 to the n minus 1. And I sum over all possible inputs x. Okay. So again, these x's, they form an orthonormal basis of the Hilbert space of n qubits, right? And so there are 2 to the n of these states. Now, this is essentially the situation here. So here I will just write it with one register, okay? But it's just for you to get the idea. So the point is here I created this big superposition which has all the possible inputs. And then remember, so the idea about this oracle here implementing the function is that I get a phase factor here. So the phase is either plus or minus, okay? So, well, the phase is either 0 or pi, but the phase factor is plus or minus, and that depends on the value of the function for that particular input x. Okay, so last time in the simple Deutsch-Jozsa algorithm, we had exactly a formula like this, maybe with a second register, but the main idea is this, right? That I can introduce these relative phases that depend on the value of the function for that particular input. So from that, it follows that if now f is constant, okay, then the output state, so if I write psi of constant, so the c now means that the function here is constant, this now is going to be 1 over root n sum over x from 0 to the n minus 1 of x, okay? Because all these phase factors are going to be the same. Either they are all +1 or they are all -1. But in any case, I can just rewrite the state like this. And if on the other hand, F is balanced, so then the output state, let me call it psi b, then this is 1 over root 2 to the n, sum over x. Okay, so obviously.
If only your mobile, you could have been dead.
Question? No, okay. So then I have this sum here, and now I have, well, I should better write these phase factors again. And so now the point of this is, so half, so half will be +1, okay? So I mean half, that means for half of the x's here, this thing will be +1, okay? And for the other half, we'll have -1, okay? And this is because the function is balanced, right? So f of x is equal to 0 for half of the inputs, and for the other half, it's equal to -1, okay? But it's very important that it's half-half, okay? Because if I look now at the overlap between psi c and psi b, okay, that is 0. And it's 0 because you see here all the phases are plus, and here I have half of plus, half of minus. So when I calculate the inner product, I get a 0. And so if the inner product of the two, these two states is 0, it follows. So then psi c and psi b are perfectly distinguishable. Okay, because they are orthogonal. So there exists a measurement which will tell me without any error whether it was that state or that state. And therefore I know if the function was constant or balanced. And again, I need to use in my circuit here, I need to use the oracle only once, right? I just prepare all this big superposition of all possible inputs via my Hadamites, and then I just measure at the output. So maybe I should just say here that these are Hadamites. Okay. Any question? Okay. So that is great. Okay, so we get an exponential separation between classical and quantum. Okay, so that's wonderful. However, there is something that is a little bit tricky here, and that is the role of errors. Because remember, one of the properties I demanded for this problem was to be able to solve it without any errors, right? So even an error of 10 to the minus 26 would not be acceptable in the terms in which I define the problem here. However, I mean, in practice, if I am able to solve a problem up to a probability of 10 to the minus 26, I'm able to solve the problem, right? Because no one cares about being wrong with such a small probability. Okay, so that's why we now need to look at the role of errors and see what happens if we make, now a sort of more reasonable analysis of the errors. And so essentially the point is that then things break down, okay? So the exponential separation disappears if we allow for an epsilon small. So yeah, that's a typical thing. No? Take a positive epsilon, but arbitrarily small probability of error. And so the idea is that for all epsilon greater than 0, well, in fact, there exists a classical algorithm which solves the problem with a constant number of uses of the oracle. And it solves the problem with probability, with probability 1 minus epsilon. Okay, and that is true for all functions. Okay, so it's just to say that, yeah, maybe I can put this in bracket. This is just true for the problem as I defined it. So what is this algorithm? Well, so the idea is evaluate f on k randomly chosen inputs x. So if we get two different outputs, then obviously f is balanced. Okay, so that is, of course, it will be wrong. And the point is that if all k outputs f of x are the same, okay, then we will guess that f is constant. Okay, and okay, because now k will be much smaller than 2 to the n, right? In fact, we said we want k to be constant, okay, because that's the number of uses of the oracle that we are going to make, okay? So since k is constant, there will be errors. Okay, because again, if I scan less than a majority of inputs, there is always a probability I get it wrong. But these errors are small. Okay, and what do we mean by small? Well, you see that the probability of an error is equal, in fact, to 1 over 2 to the k. Okay, so what is the probability that my k randomly chosen input all give the same output value of the function when the function is balanced? Well, this is 1 over 2 to the k. Okay. And so you see this thing drops extremely quickly. And so it follows that for all epsilon positive, take 1 to the k smaller than epsilon. So this is my probability of error, right? And so so if I do that, then I'm good, right? Because then my probability of success is always larger than this, than 1 minus epsilon. And the point is that, so importantly, K does not, so K is independent of N, okay? So indeed, with a constant number of uses of the oracle, I solved the problem. So of course, this constant number, so which is given by K here, it might be large. Maybe it's 1 million, maybe it's 10 millions or 1 billion. But remember, I mean, in complexity theory, we just care about the scaling, right? So we don't care about constants. Okay, so here, this exponential separation I previously demonstrated with this generalized Deutsch-Jose algorithm, we see that as soon as we allow for errors, and that can be any epsilon error, we lose the exponential separation, because there exists this classical algorithm which solves the problem with constant error and constant number of uses, sorry, with fixed error and constant number of uses of the oracle. Does it make sense? Okay, good. So let me continue. So in a sense, the continuation of this is, let's do better, okay? So what we want, so we want an exponential separation between classical and quantum. So this is classical versus quantum, even in the case where errors are allowed, even with errors. Okay, and that brings us to the next problem, which is the problem of Simon. Okay. So here is how it works. So we are now going to look at functions which take, why is it written like this? Sorry, let me just use the same notation as before. It's written. So it's a function that takes an n-bit input string, but gives an n-bit output string as well. Okay, so it's, yes?
I have a still image. I'm the only one? I don't.
No, you're right. I also do have, in fact, a still image. Thanks.
Welcome.
What's going on? Aha, so my phone decided to die. That's strange. Okay, then I would suggest let's do a small break here. It's actually a good time to make a break, and continue the recording. And I reshare. Okay, so all this is good. Yes, and now we were defining this problem of Simon before my phone, for some reason, died out. Okay, now, all right, so we are going to, so let's just use some notation. We are going to refer to these n-bit string as x, and the output here will be f of x. This we are going to call y. No, is that a good notation? Well, okay, I try like this. All right, and just to mention it, there is a small hypothesis here, namely that f is in P. Okay, so computing this function is relatively easy. Now, despite the fact that computing the function is easy, we can still define a problem that is hard classically. So the problem is the following. So it's again an oracle problem. So given an unknown f, and we will make it a bit clearer later what f, in which category f is, decide or find out if or whether, so one, f is bijective. Okay, so what we mean by bijective is that f of x is different than, yeah, maybe this is now my notation. Well, okay, never mind. Let's do it like this. So, yeah, sometimes y is used to refer that the output string here is just another input string. But okay, I guess depending on the context, it is clear which one it is. So here, so you see I have two different inputs, x and y. And so I'm saying that the function is bijective when the outputs are different for all inputs that are different. Okay, so it's just normal bijectivity if you want, but for functions defined on bit strings. And then I have another possibility, namely that f is not bijective, and then it will be periodic. So what I mean by periodic is that f of x will be equal to f of y whenever x is equal to y plus some bit string c. Okay, and so here we say f has a period given by c, and okay, when just to make it clear what this thing here means, so when we say y plus c, this means addition modulo 2 bitwise. Okay, so this is going to be an n bit string where you have y0 plus c0, okay, until the end where you have yn minus 1 plus cn minus 1. Okay, is that clear? So this is, yes, this is addition mod 2 for every bit, right? So bitwise. Okay, so here is our problem, and you see it's very similar in spirit to what we had before, and maybe remark again. So so we have promise that the unknown f that is given is either bijective or periodic. So we have promised that f is either 1 or 2. Okay, there could be functions that are none of these, that don't have any of these two properties, but here we just consider them. Okay, and in fact we are going to require another thing. In case f is periodic, we demand to find the period c. Okay, so that is, it's also something important. All right, so this defines our problem of Simon. So first, well, we have to look again classically. And here, classically, one can prove that the number of uses of the oracle or number of evaluations grows exponentially. Okay, and this thing here, this is hard to prove. So in fact, in his paper, Simon, I mean, the main challenge of Simon was to construct this problem and then prove that it is a hard problem classically. The quantum solution, as you will see in a minute, is relatively straightforward, or in a sense natural, given the tools that we know and that we have at our disposal. But you know, proving that you can do it quantum mechanically is only half of the challenge, right? You also have to prove that classically the problem is really difficult. And so, in a sense, that was one of the main, at least technical challenges in the paper of Simon. So, of course, here we will not go through the proof. If you want, the idea is, so the intuition maybe, is that, so finding a period, you know, this is more or less like doing a Fourier transform. Okay, and a Fourier transform, this is very time consuming. Okay, or just in computer science language, doing a Fourier transform is hard. Okay, so now let's see how we go. No, sorry, I should now say quantum mechanically. What do we have? Well, we have Simon's algorithm, and this one's it solves the problem in poly and evaluations. Yeah, sorry, my sentence is a bit weird. Let me make a sentence. So this requires only poly and evaluations. Okay, so we get a separation that is exponential, and perhaps what I should remark here for the classical case, and that the point is that this is true even with errors. Okay, so if you fix a constant error rate that is independent of the size of the problem, you still require an exponential number of calls of the oracle. Okay, and classically, and quantum mechanically, this is poly n. So we have an exponential gap again. So let's look at the quantum algorithm, and maybe we first need to discuss some ingredient, which is the Hadamard transform. That will be our main ingredient. So let's define it. So this is a unitary on n qubit register. And in fact, it's simple because this thing is just applying the Hadamard to each qubit. So in a sense, the Hadamard transform is something that we have used already. Okay, so we can even have a little graphical notation for it. Might be convenient. Sorry, so this is U of H, okay? And so this takes, here we have n qubits, and we have everything coming out here. And so this is nothing but just applying Hadamards on each qubit individually. Okay, so this is really the thing we always did so far when we started our algorithm, right? So on the register that encodes the input of the function, we started by doing this. But now we are going to use it in a slightly different way. Namely, we are going to use it because u of h will be essentially doing a sort of Fourier transform. So let's look at this. So when you apply u of h on some bit string x, so I claim that what you get is the following thing. So you get a big superpositions of the following. So you sum over y's. Okay, so so this notation here means that I sum over all possible bit strings y. Okay, so this is again, again, there are 2 to the n out of these, right? So it's just a simpler way of writing the sum. And now, well, you see what happens is that now I obtain this huge superposition here, and the phase coefficients, they are all given, essentially, they depend on the inner product between x and y. Okay? And so maybe we should write what is this inner product. So x dot y means x0, y0 plus x1, y1, and so on. Okay, and xj, yj, they are the components of these bit strings. And so it's really just a sort of binary scalar product. Okay. Okay, and so we can actually check that. Well, in a sense, we know already one case of the use of this Hadamard transform. It's when the input state here is a 0, right? When it's the first state in the orthonormal basis. And so in that case, we expect to have a big superposition of all possible inputs. And indeed, so if we look at this formula, if x is 0 here, well then it's clear that all these coefficients are going to be the same and they will be just +1. And then indeed we have this big superposition of all possible states y with the same coefficient. But okay, maybe it's worth just checking it a bit more. So let me do the case where I have 2 qubits, sorry, 2 bits. Well, okay, it's the same, 2 qubits also. So imagine I have the initial state 0. That's in fact the case that we just described. So now if I have a u of h on 0, 0, this gives me a 1/2. I should sum now y over, so y can take the values 0, 0, 0, 1, 1, 0, 1, 1. Let me write it like this. And I have to sum this thing. Okay, now here my string x is 0, right, for all entries. So again, it doesn't matter here what is the value of y. That phase factor is always +1. So that thing is just equal to half of 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. Okay, and you see here I can pull a 0 out for the first system, and then I have a 0 plus 1, so that is like a plus. Here I can pull out a 1 for the first system, and I have also a 0 plus 1, and so therefore I can take the plus out, and essentially I just end up with a state that is plus times a plus. And that, of course, is equal to Hadamard applied on my state 0, 0. Okay, so, okay, this example shows it works. We could just do another one. Could also do the 0, 1, which is maybe a bit less trivial. So if I do a u of h of 0, 1, what do I get? Well, in fact, Okay, I'm not going to recopy this formula, but if I take it from here, right, I should also get this superposition with all these 4 terms here. And now I just need to look at what are the coefficients, right? So the 0, 0 term, okay, so here this is the y term, right? So the 0, 0 term doesn't care what x is, so that gives me a plus coefficient here. Now the 0, 1, so here I should take the scalar product of 0, 1 with 0, 1, okay, 1 being for the x, 1 being for the y. Now that gives me a minus, okay, because now this scalar product is 1. Now the next case here gives me a plus sign because in a sense they are orthogonal, so the scalar product is 0, and here I get a minus sign. Okay. Okay, and so now what state do I have here? Well, you can easily figure out that the state you have is a plus, a tensor, a minus. Okay, you see that you have these minus signs appearing here. And indeed, that is nothing but Hadamard applied twice to 0, 1. Okay, does it make sense? So, okay, we don't go to a full proof of this, but I guess you see the idea here. So now let's go through the algorithm. So now we go through Simon's algorithm because essentially this Hadamard transform is really what we need. So we have our big box here, our oracle for U of f. And so we have 2 registers. On the first register, we are going to do a Hadamard transform. So that is as usual. And well, okay, on the second register, we do nothing. Here we start with the states 0. Now, what do we do here? And on the second register, we do nothing at the output. We're just going to measure here. And now we do a trick. So this is essentially the main novelty here, is that we apply our Hadamard transform again on the output of the first register. Okay, so this is our circuit. And now essentially we will just go through the different stages of this circuit and see what happens. Okay, so first we have this stage here. So this is time 1. So at time 1, we just have 2 n qubit registers, and they are initialized in the state 0, 0. Okay. All right. Now comes time 2, which is here. At time 2, now I apply U of h to first register. Okay, so what do I get? Well, I start from that state, and now I get my usual big superposition. So this is the sum over x of x 0. Okay. So here I write 0 with a bar, which means that it's the that all n qubits are in the state 0, right? So now I go to the third stage, 3 here. So this is apply U of f. So this is to both registers now. So essentially I apply U of f to that thing. Well, I just need to know what happens when I apply U of f to every x. This gives me x f of x. Okay, because now, since my function can be periodic, right, in my problem, I need to do that trick in order to be able to implement it with a unitary. So I have the 2 registers and keep the input in the first. And so the point is my state now will be u of f applied to 2 to the n over 2 sum over x, x 0, and that is simply 1 over 2 n over 2 sum x, x, f of x. Okay, so far I really didn't do anything really different from before. I just applied the basic recipes, and now things get more interesting when I do this step 4. So now I do UH on first register. Okay, and so now I should take that state. Okay, and I should now apply UH on the first register. So what I get is that I get 1 over 2 to the n. Remember now that for every x here, I have a sum over all possible inputs. So that's why you see I no longer have the root of 2 to the n, but I have 1 over 2 to the n. And so now, well, sorry. So first I have my sum over x. It's not very nice. Sum over x. And now inside I have a new sum, which will be my sum over y. And now I just need to use the definition of this Hadamard transform. And I have the following thing. Okay. So again, the second register didn't change, right? I didn't apply anything on it. So here I still have my f of x, who is my big sum on x. But because I applied UH on the first register, I have this new sum here. So you see that this thing here, this comes from, this is u of h applied to x. Okay. Well, up to normalization, right? There is a factor that I pulled out in the front here. Is that clear? Good, okay. So now I will move to the next step, but run out of paper. So get some more. Okay. All right, so now I come to the fifth and last point. Let me write it here again. So this is my measurements now of the register. So this is the final stage. So 5 is the final stage, and here I measure registers at the output. Okay, and this measurement, it will be done. This is a measurement in the computational basis, right? So in the orthonormal basis of X states. Okay, now let's. So here is really the main point. So I need to look carefully. So first, I'm going to look what happens if F is bijective. Okay, and then my point is that the result of my measurement on register 2, so the second register, this will be random. Okay, so random means between 0 and 2 to the n minus 1. And so why is that the case? Well, this is it must be the case, right? Because imagine so this is my output state here. Now, if I measure the second register, I can find here all the values of f of x, right? There is a big sum over all x's, so all output values f of x appear. And because the function is bijective, well, it covers all the output space, right? So all n-bit string outputs are possible, right, for f of x. Okay? So here, there is really an implication, right? So maybe I should write it again. So all outputs f of x are possible. Well, in fact, sorry, maybe it's not the right way of saying it. So the point is the output f of x can take any value between 0 and 2 to the n minus 1, right? All right, so we are going to say the output of this measurement is, let me call it x, and this is equal to f of k. Okay, so there is some input k which corresponds via this function to this output x. So my total state is what? Well, it's now the sum over 2 to the n over 2. Sum over y minus 1 k times y, y f of k. Okay, so I just took that formula. So here is the state before the measurement, and there are all possible values of x that appear. Let me say, so now I make a measurement here, and I find, let me call this output x. Yeah, sorry, maybe this is not the best notation, but still, let me call this output x, and this corresponds to some input k. So of course, now I have collapsed this sum here onto only one term, right? Which is the term for x being equal to k. So that's why now my total state has only one sum. It still has this, right? Because I didn't touch the first register. But of course, all x's here now collapse to k. And that's why I have this form, okay, with a k here and a k there. All right. So the point is now, if I now measure the first register, I also get a randomly uniform output. Okay, because, well, you see that here there are all possible y's that appear, right? Each one has a different phase factor, but all y's appear. So my conclusion of this is that when f is bijective, measurement results are all uniformly are all uniformly random. Okay, so there is really just no structure in what I see at the output. Okay, now let's move to the second case, when the function is periodic, and then things get much more interesting.
Sorry?
Yes?
Can I have a question?
Sure.
And why did we say that the possible outcomes of f are between 0 and 2n minus 1, 2 to the n minus 1, because I thought the values that could take the function f is just 0 and 1. I'm confused.
No, that was before. You're right. Before, when we looked at the Deutsch-Josa type problems, the output of the function was binary, so just a bit.
Okay.
But here, so remember, this is our definition of the problem of Simon. Here, the output is also an n-bit string.
Okay.
Okay, so this is an important difference.
Okay, okay.
Okay,
Yes.
makes sense?
Yes, thank you.
Mm-hmm. And you see, I mean, this must be the case because otherwise this idea of periodicity doesn't make sense, right?
Yeah, yeah, of course.
Okay, good. So let's move back. All right, so now we move to the case where f is periodic. So if f is periodic, so let's do a sort of similar reasoning, right? I mean, you see the reasoning before in the case f is bijective was a bit maybe indirect somehow, because we could have just guessed right from the beginning that the outputs must be uniformly random. But the approach we will reuse here, and here it will give us much more insight to the structure. So let's first start with measure of the second register again. So this measure, let's say it gives an output, which I call, let me call it x prime, such that x prime is equal to f of k, okay? Now, since f is periodic, then I know that this particular output x prime, it also corresponds to another possible input. Sorry, this is just noise here. Namely, f of k plus the period c, right? That's the definition of the periodicity. Okay, so now the difference is that given an output for the second register, so given a value of the function, there are twice as many inputs that are associated to that output. Okay, so that will change the structure. It will still be true that the measurement of the second register is still randomly uniform, because I can find all output values x prime. But now I have a new structure, and that will influence the result of the measurement on the first register. Okay, so maybe let's remark here that this is still randomly uniform. Okay, this is my measurement of R2, but that's not really our main point. So now let's look at the state of the first register after making the measurement on second register. Okay, so we said we do the measurement on the second register, we find output x prime, and that can correspond to two inputs, k and k plus c. So now how do we write the state? Well, we have a 1 over 2 to the n over 2. Remember, we have again this sum over y. And now what do we have? Well, we have minus 1 k dot y, okay? Let me put it here on purpose. So now I have the term y, and here I have f of k. Okay, so that is my value x prime that I found. Okay, I will just write it like this here. And so in the first register, where I have definitely this term here that I wrote, sum over y, with this coefficient here, where the input x has been set to k, right, which correspond to my output. Now, however, because of the periodicity of f, there must be another input, namely k plus c, that also appears here, right? Because this input corresponds to the same value of the function. So here, I need to add -1 to the power k plus c, and this scalar product with y. Okay, so I hope this is readable. So this is a k plus c scalar product with y. Okay, because k and k plus c, they are the two possible inputs that corresponds to that output. And so if I want to be rigorous, I should probably put a 1/√2 here because now I have two terms, right? Okay, very good. And now, so the point will be that I will have to massage a little bit this expression to see exactly what happens. So from now on, let me just forget about these coefficients here. I'm just interested in the structure of this sum. So I have a sum over y. Let me pull out a -1 over k dot y. And now I have a 1 plus a -1 times c dot y. Okay, so I just pull out this term. And now you see that everything, so this is the interesting part. Okay, because you see, obviously this term here can take the value either 0 or 2, okay? And which value it takes depends really on this scalar product here between c and y. Okay, so let me look at this term. So 1 plus -1 c dot y. So that thing, as I mentioned before, it can be equal to 0. And that is the case if c dot y is equal to 1. Okay, so in this case, I have a destructive interference, right? Because so if the y is such, right here I have this huge sum over y, but for all the y's that satisfy this relation here, this coefficient will be 0, right? So it means that these terms, they sort of destructively interfere. They disappear from the state, right? They have 0 amplitude. Now, that means that the remaining terms, they must have a higher amplitude, right? Which is the case because then this coefficient here is a 2. And remember, this is an amplitude of probability, right? So later when you compute the probabilities, they will be multiplied by 4, actually. Now, this term here is equal to 2 whenever c dot y is 0. Okay? So that means in practice now, suppose I make measurements on the first register, then there are only certain y's that can appear, right? Because all the y's for which c dot y is 1, they have amplitude 0, okay? So these never appear. The only y's that appear are those for which c dot y is 0. And that is the main thing I need to use here. So I run again out of paper. Okay, let me take a big pile now just to be safe. So the conclusion of this is that the measurement of first register gives only output y's such that c dot y is equal to 0, okay? The others, they disappear by destructive interference. So this is essentially what I need, okay? So I'm essentially done now. Now we have to see what to do exactly with that. The point is that, so the algorithm will be a probabilistic one. Okay, because clearly you see if I run this procedure, well, okay, I get, at the end, I get one value of y from my measurement on the first register. Now from this one value, of course I know nothing, right? This doesn't tell me if the function is bijective or periodic. So we need to run the algorithm many times. So need to run algorithm many times. So yeah, okay, so yeah, here this would be the total algorithm, right, which consists in running the above procedure. Maybe I should. So this is run the above procedure up many times. Okay, so if I do that, so in fact I should repeat more or less n times. Sorry, it's not true. Let's say m times the procedure, such that I get at least n different results y, let me call them yi, okay? And I goes from 1 to n here, okay? So again, right, so in every repetition of this procedure, in every round, my measurement of register 1 will provide me with one value here of y, okay? But this is a huge sum, remember. So even if I have this structure here with some destructive interference, there are still a huge number of terms in this sum. So every time I measure, I run the algorithm, I have a certain chance of finding those y's here which satisfy this relation, but there are many of these, right? So if I run it a sufficient number of times, clearly I will find n different values, which I call yi. So once I have that, then I solve the following problem. I solve the problem that yi dot c must be equal 0 mod 2, okay? And that is for all I in 1 to n, okay? And this, which gives me C. Okay. So finally.
Excuse me?
Yes?
Is there any relation between M and N?
No, because it's probabilistic, right?
Okay.
I mean, you see, okay, there is a small probability that you get the same yi, but I mean, this thing is really super large here, so
M should be just a large number of times, basically.
Exactly. But M is certainly certainly polynomial with n. Okay.
Okay.
I guess you could say something clearer about this m, but okay, you just need to notice that this number of times is it's just not exponential with n. It's, you know,
Okay.
maybe it's even linear, I guess. Not sure, but okay, it's a polynomial. That's the important thing.
Okay, thanks.
So finally, what we do is take a random input x and check that f of x is equal to f of x plus c. Okay, so in a sense here, this is two more uses of Oracle. Okay, but that two more is just irrelevant. And so if yes, well, then we know, right? Then f is periodic, and we know the period. That was the challenge, right? And so otherwise, then f is bijective. Bijective. Okay. And yeah, and that's it. So are there any questions on this? Okay, so maybe let me say a couple of more words on this. So now you see in this problem, what we managed to do is we managed somehow to evaluate a global property of a function, namely the period here. And that we did in a very efficient way, essentially via this Hadamard transform. Now, in fact, if you look a bit closer at this, you see, so what is this Hadamard transform doing? Well, it is, you see, essentially, let me go back to it, yes. Essentially, you see this thing is kind of computing a sort of discrete Fourier transform, right? So it's not quite the usual Fourier transform, but you see this thing here. It can be seen as a sort of analog of a Fourier transform. And this thing you can do with a linear number of gates, and you can also do that on a superposition of all inputs x, right? Which is why the thing becomes really powerful. And now the point is, and this is also true in the history, once you have seen this algorithm of Simon, and you understand that that quantum circuits are good for computing efficiently the period of some function, well, then you, in a sense, you are directly led to the idea of using quantum computation for factoring, because solving the problem of factoring is in fact equivalent to finding the period of some function. So this will no longer be you know, function, I mean, here we have a bit of a strange idea of a period, right? Because everything is modulo 2, but that is not a limitation. This is only the definition of this problem here. And so essentially what we will do next time when we look at Shor's algorithm is to, you know, use similar ideas, but now on a problem that is not of Oracle form, right? It's a problem where you have an abstract function that is given, and you have to try to compute you have to try to find its period, okay? All right, so I guess it's a good time to stop. We're a bit early, but that doesn't matter. So are there any questions?
Yeah, I have a question.
Yes.
So does the algorithm break, I guess it does, if we allow for the function not to be bijective? So here we have the choice, either it's bijective or periodic.
Uh-huh.
If it's allowed to be just any function, it breaks, I guess.
Yes.
Where does it break?
Because, yeah, it's a good question. So the point is it breaks because you see, so if the function is different, right? It's not bijective and it's not periodic. So it means that for some x, I have this property maybe, but not for all x, right?
Right.
So when I write here, you see, it might be that I calculate this thing and I find that it's true.
All right.
But maybe there is another x for which it's not true. And so therefore, you know, that's why I need to restrict those non-periodic functions to be bijective, because then I can find out by checking this on only one input.
Is it enough that it is injective, maybe? Necessary. Yeah.
Good question.
Probably an annoying question, sorry.
No, it's good. It's good. For me, it's good to also think a bit more about these questions. Yeah, I would say so, no, but okay, I'll tell you next week. Let me,
Right.
I don't want to tell you something silly, but I would say it should be.
All right, thanks.
No problem. No, but sorry, I'm stupid. No, it must be because the output space has the same dimension as the input space, right? So yeah, you need to map all inputs to different outputs, and then you see. So then by construction, the function is also surjective because it covers all the output space, and then it's bijective. Yes.
All right.
Yeah.
Yeah, thanks.
Good. Any other question?
Here in all the dot products that we're doing, the C times Y and Y dot X, those are modulus 2, right?
Yeah, everything is modulo 2.
Okay, good.
It sounds like we finished right on time before the chaos comes back. But still, we are safe still for a couple of minutes. So if you still have questions, I'm here.
No, but actually, I do have the same question again. Sorry.
Okay.
The value of a function, I see that is an n bit, right?
Yes.
So why do we say again that it's a value between 0 and 2n to the minus 1? It should be then like, why is it a normal number and it's not like an n bit?
Well, it's an n-bit string, no? The output, the input and the outputs, they are n-bit strings.
Yes, and it says the result of the measurement on register 2 is between 0 and 2n to the minus 1.
Yeah, because I make a measurement in the basis of these orthonormal 2n states, right?
Oh, okay. Yeah, because I thought it should be like between 0 and 1. Because
no, because yes,
it's just the second. It's just second registers.
Yeah. So if you look at this, for instance, right? So each of these things here is an n-qubit register, right?
Yes. Yes.
So it can be the what we call the computational basis is the basis where every qubit here can be either in the state 0 or 1.
Exactly. Yes.
So it's equivalent to, you know, n bit strings.
Yes.
And so there are 2 to the n values, right?
Okay. So we are adding all the values.
No, so this is the binary representation, right?
Okay. I get it. Yes.
Yes. Okay.
Yes, yeah, I get it. Okay, thank you.
So sorry, I saw there was something in the chat before. Let me see if I can see it.
No, don't worry. It's just about the question before, because like if we think about binary numbers number represented in binary terms,
Yes.
we get this series like sum over 2 at the power k from k is equal to 0 to
yeah, exactly.
1 to n. This is the reason why we have 2 power n minus 1. So, yeah.
Okay, yes. Yes. I was just not thinking that it was a binary representation.
Yeah, sure. No, this is just a computer
confusion,
science language, but yeah.
Okay.
Yeah, I should have maybe made it clear that we are always using that.
No, it's okay. It's just I'm not used to it, maybe.
Yeah, no, sure. It's if you're a physicist, it's the first time.
Yes, thank you.
All right, so if there are no further questions, maybe let me stop the recording.